And that's f of w equals 1 over 2 pi I times the integral of gamma of f of z over z minus w dz. And this is, of course, you need, gamma is like a curve with a positive orientation, simple, closed, smooth, piecewise smooth. It can have some cusps here and there, it can have some, but it's like completely closed, meaning the starting and ending point are the same. And W is somewhere inside the curve. And then F is holomorphic in some region that contains the whole curve. And that region doesn't have any holes in it or anything. Okay, so this is it right there. Okay, now if you take the derivative of this with respect to W, then over on the left-hand side, you get F prime, right? So you get this F prime of W, the derivative of W. And on the right-hand side, just take that right inside the integral. And the derivative of, so just treat a z as a constant, okay? So if you have like, so this denominator, and just treat the f of z as a constant. So this denominator is like z minus w to the minus 1, right? If you take the partial of this with respect to w, what do you get?
One over c minus w squared.
Yes, that's what you're going to get. So that is this piece right here, see? So then we have Cauchy's integral formula for derivatives. And if you take another derivative, then what's going to happen there is like if you have z minus w squared to the minus 2, I'm sorry, 1 over z minus w squared, then you're going to have a 2 come out, right? You're going to have a 2 and then z minus w to the negative 3, okay, which is what we get right here. So this piece is that, but do you notice that there's no 2 right here because that 2 got knocked out, right? The 2 canceled with this 2. Okay, and in general, you're going to have so this is the first and the second derivatives. The nth derivative is going to be n factorial over 2 pi I f of z over z minus w. Okay, so the first derivative has a 2, the second derivative has a 3, so the nth derivative will have an n plus 1. Okay, so this right here is the general formula for the derivatives, right there. Okay, this also leads to something called Cauchy's inequalities. And let me explain what that is. And leads to a lot of interesting results, which we'll get to later in the section. So, so here we have Cauchy's integral formulas for derivatives. Okay. So here we set that up like. Okay, so this is the formula that I just came up with. Okay, so the interesting thing is if you let gamma be the circle of radius r centered at W. Okay, so a parameterization would be, let's see, let me see if you guys remember. You remember how to parameterize a circle whose radius is r, whose center is W, whose center is a particular point? How to parameterize that circle? Does anybody remember?
It would be W plus e to the IR t or something. Art. Oh, REIT.
RE to the IT, yes. So that, and then the parameterization would be from 0 to 2 pi. Okay, so if we do that parameterization, okay, then gamma prime of t is going to be, that's 0. So this is going to be IR e to the IT, right? So that's telling us that the nth derivative of W is going to be, so if we use the definition of the integral and we apply this right here, that's going to go from 0 to 2 pi on this interval there. And then here we have f of, the z gets replaced with this. All the z's get replaced with these. And then including, hold on, including this z right here. Oops. Including this z. This z gets replaced with w plus r e to the it. And then there's a minus w though, so wow. And then this dz gets replaced with I, r to the it, dt. Okay, great. So the w's are going to cancel right there. And you're going to have f of w plus r e to the it over, okay, this is going to be r to the n plus 1. But here's an r e to the it, right? It's going to cancel this plus 1 off because it's going to take out exactly one r to e to the it piece. Okay. Oh, I forgot. I can't believe I forgot this piece right here. N factorial over 2 pi I. I'm sorry. I was so excited about this. Okay, so this is r to the n, e to the I, and t, dt. Okay, so that's your nth derivative at w right there. There's a couple of directions I want to go with this really quickly. The first one is if you take the modulus. Oh, I messed up something. There's this I here, right? Okay, so this I and this I is going to cancel each other out, right? So that means that this is just going to go away. Okay. Okay, so the i's are going to cancel. Okay, those i's will cancel because this is the numerator up to denominator. Okay, so we just get this. Okay, now if you take the modulus, okay, well this is just going to be n factorial over 2 pi I, and then here we have the integral from 0 to 2 pi of the modulus of f of w plus r e to the it. Actually, don't take the modulus there. I'm not supposed to take the modulus inside. Over r to the n e to the int dt. Okay, so there's the ML inequality. Now they have this r to the n. This is just a constant, so that comes all the way out. And you have the ML inequality, where m was the maximum value of this, of the modulus, which, if you look at, so m is equal to the maximum of the modulus of f of w plus r e to the it over e to the int. This is just going to be 1 because this is always 1 in modulus, right? So, and then the L is the length of the interval, which is 2 pi. Okay. So it's 2 pi minus 0. Okay, so that's 2 pi, so you get 2 n factorial. And then m is going to be the maximum of f of w plus r e to the it. And then the L is going to be 2 pi. Okay, and then of course these 2 pi's are going to cancel each other off. So essentially, the nth derivative is less than or equal to n factorial times m over r to the n. Okay? This is called Cauchy's inequality, and m is the maximum value of the modulus. And this is on a circle of radius r. So you're only looking at the maximum value of the modulus on this circle right here to get the centered at w. Well, centered at w. So I guess I drew this wrong. I didn't need that coordinate axes. Okay, I'll just put w in the middle. So this could be anywhere, you know, just centered at w. Okay. So the modulus of the nth derivative is less than or equal to this. Okay, this is these are Cauchy's inequalities because it was 1 for each value of w, of course. Okay, so Cauchy's inequalities. Okay, now also what I need to do is show you how to we'll come back and use this later. But I need to show you how you exploit these two right here. So let's do a couple of problems. So the first one would be to find the integral gamma of cosine of 3z over z minus pi over 2 squared. Okay, so and let me draw a picture of what gamma. I'll just draw a picture of what gamma looks like. So you have, where is this not holomorphic? Where is this not holomorphic?
Pi over 2.
Yeah, pi over 2. So pi over 2 is right here. Okay, then I'm just gonna draw a gamma that that's simple and closed and a positive orientation, and then pi over 2 is inside, okay? Because if pi over 2 is outside of this, then the integral is going to be 0, right? So we're not interested in the easy ones. Okay, so let me recall the, since the problem that we want to do has a square in the denominator, let me point to this formula right here. Okay, this formula here for the first derivative. Okay, so let me write that down here for comparison. So the first derivative is equal to 1 over 2 pi I times the integral of f of z over z minus w dz. Okay, so that means, that if you solve for this piece right here, oh, this is squared, I'm sorry. Okay, what is it if you solve for this?
2 pi I times derivative of f w.
Yeah, f of w, not z. Okay, great. So let's do some identification and try. So this right here, you should recognize that this is similar to what we have here. Okay, what is w though?
Pi half.
Exactly. And what is f of z?
Cosine 3c.
Great. So our answer is 2 pi I times f prime of w. Okay, so what's f prime of z?
3 sine 3c.
Yeah, negative 3 sine 3z, right?
Mm-hmm.
Okay, so f prime of w, which is pi over 2, is going to be negative 3 sine of 3 pi over 2. Okay, what's sine of 3 pi over 2? Well, 3 pi over 2 is down here, right?
Negative
So,
1.
yeah, it's negative 1, right? So this is negative 3 times. So that part's 3, which means that this integral is going to be 2 pi I times 3, or 6 pi I. Okay, because this 3 right here goes in there for the f prime of w. Okay, so that's one way that you can exploit it. Let me give you some other examples. Okay, so we're taking the integral, and this time we're going to go over the circle of center is 0 at radius 2. And the numerator will have exponential of z, and in the denominator we have z plus 4i and z minus I dz. Okay, so now there's no squares here. So what do you think? What should be the first thing that you do when you have something like this? Do you guys remember?
partial separate, is it?
Separate it? Oh,
Yeah.
partial fraction decomposition?
Regression, yeah.
Okay, that's a good thought, but in this case, you don't have to do that. Okay, so let's see. What's the first thing I did with the previous problem? Well, I wrote this down, and then what I write next? Next I wrote this, right? Okay, so it's really important. Probably the most important thing, the first piece of information that's going to be the most valuable is to draw a picture. Okay. So what should that picture contain? Okay, so the first thing. So in the picture, I want this. First of all, I want that. And that's going to be the circle of center of radius 2, centered at the origin. Okay. Put a couple of points there to make it look legit. Now, what else do I want in the picture? Yeah, so this denominator this piece of the denominator is 0 when you're at I, and I is right there. And what else do I want?
Negative 4i.
And negative 4i. Okay, so this one is I, and this one I want negative 4i. And negative 4i is down here, right?
Mm-hmm.
So that means that we don't have to worry about the negative 4i.
Mm-hmm.
Because it's not gonna, this piece right here doesn't affect the, it doesn't affect, like I can take a region like that, and this curve's completely in there, and the only bad point is, the only point where it's not, where this is not holomorphic is I. This doesn't, so this part doesn't really affect it, okay? It doesn't mess us up. Okay, so that means that you can look at it this way. I can take the numerator to be exponential of z. Let me write it this way. Times z plus 4i to the minus 1. Dang it, I don't like that I right there. Oh, I'm just making everything really bad. And then just have a z minus I in the denominator. That's emphasizing that this is the only place where we have problems, right? Okay, so, and then compare this with Cauchy's integral formula. Which is, if you have, this is 2 pi I times f of w, right? So that was Cauchy's integral formula. So in Cauchy's integral formula, what's our w going to be?
I.
Exactly. And then what's our f of f going to be?
Exponent of z and the z plus 4i to negative 1.
Yeah, the exponential z over z plus 4i. Okay, so f of w is going to be f of I, which is going to be xt of I over I plus 4. Dang, what's the xt of I? Cosine 1 plus I sine 1? What the? Oh my goodness. Okay, so this is going to be 2 pi I times all that. Well, at least the i's cancel, right? Yay. I'm glad those were got out of the way. Say 2 pi over 5 times cosine 1 plus I sine 1. Ah. Okay, one more quick example, and then we'll move on and talk about more things. Let's try orange. Okay, so find, is that orange or brown? Oh well. Okay, so we're gonna have, no, not this one. It's gonna be sine of z over z minus pi over 2 squared. And here's pi over 2. Well, we'll have this be just a curve like that. Or we can, actually, what we can do, we can actually make it equal to the circle whose center is 0 and whose radius is 3. Okay, there we go. So pi over 2 is about, so pi is just about 3.1 something. So 3.1 something over 2, that's like 1.5. So for sure, if we go out to 3, then that's gonna contain that, right? So I can just be that. Okay. So what's this going to be equal to? What's the formula say? Is it the first derivative or the second derivative? Okay, so if you go look at the first page, you have the second derivative of w equals 1 over pi I times the integral f of z over z minus w cubed dz. Because we have wait a minute. I copied it down wrong. Oops. That is supposed to be a cube right here. Oops. Sorry about that. I meant to write a 3 there. Okay, so that means that the integral part, this piece here, which is what we have there, is going to be what? It's going to be pi I times f double prime of w times the second derivative evaluated at w. Okay, so what is f of z in this case?
Sine z.
Great, sine z. And so what do we have to do with this sine z?
Cosine z.
Take a couple of derivatives, right?
Mm-hmm. Right, derivative sine z.
And then W is pi over 2, right?
Mm-hmm.
So that's -1, right? So that's just going to be, oh,
I
wait.
think you missed I.
Yeah. -pi. Okay, so let's go back and take a look at a few things here that we skipped over. Okay, so those two formulas are pretty important. I just wanted to make sure you understand that. Well, the homework will force you to understand that. So those two formulas are pretty important. Okay, so the next page is just a bunch of examples. It's good to go through those. This corollary here is kind of interesting. If f is differentiable in a region G, then f is infinitely differentiable in G. Okay, so differentiable implies, or holomorphic implies infinitely differentiable. It means you can, and all partials of f with respect to x and y exist and are continuous. This is because we have a formula for the derivative, right? That is not really finding any derivatives, right? This is the formula for the derivative right here. So that means if this is holomorphic, then basically this is a formula for all derivatives right here. Just like it's just that interval there. Okay, so that's basically that part. Okay, so we have Morera's theorem. Supposes f is continuous and the integral is 0 for all, then f is holomorphic. Okay, the definition of simply connected, it's homotopic to 0, very close path. If it has, simply connected means it has no holes. Now, an alternate definition of simply connected would be that the complement is connected. Okay, so something that's not connected would be like if you had, okay, that's connected if we just take an inside there. But if you like exclude this guy, a bit of this out, and you're only taking like that, so you got like Swiss cheese, then this is not, this is connected, but it's not simply connected. I'm sorry. It's not simply connected because this piece is not included. Okay, and then like if you had if you could place a string that goes, it's entirely in here in a circle or rubber band or something, and be around that. And in order to contract the rubber band, you'd have to pull it through that region that's not in there, through that part that's not in there. Okay, another way that simply connected, or the way that simply connected is usually defined, is that the complement is connected. And here, the complement would be everything outside here plus this right here. And see, the red is not connected, right? Because this is apart from the rest, right? Okay. Corollary 5.8. Okay, every homomorphic function on a simply connected region has an antiderivative. I want to say something about that one in regards to, this is corollary 5.8. Every holomorphic function has an antiderivative in G. So I want to say something about that. One of the exercises, I'll point this out really quickly. No. Just a hint for you guys. So this is number 5.8. It says show that exp of sine z has an antiderivative on the complex numbers. So if you look at that, like it's kind of like, it's like if you're in calculus and you're like, okay, take the antiderivative of this, then you're like, what the? This is something that you, and probably if you put this into Wolfram alpha or something, they wouldn't be able to give you an antiderivative. They wouldn't be able to come up with it. Okay, and so, so coming up with it is not going to work. But what you can do to do this problem is use corollary 5.8. Okay, and that tells you that just kind of says that it has an antiderivative, because if you can show that it's holomorphic, and then this question right here says, what is it? And I would say look at Theorem 415 for that part. Okay. So exp of sine z exp of sine z, corollary 5.8, every holomorphic function has an antiderivative. So you should show that that function, exp of sine z, is holomorphic. In fact, it's entire. And so there's a couple ways you can show that. Okay, one of them is just by claiming it's a composition of entire functions, and the other one is by just doing the Cauchy-Riemann equations. Okay, so you can do whichever one is more fun. Yeah, that's what you should do. Just choose the method that's more fun and use that one. Okay. Let's see, where are we? Okay, so next thing I want to do is, an interesting thing happens if we take the Cauchy's formulas to the limit. Okay, so you recall earlier that I showed you Cauchy's inequalities. Cauchy's inequalities. And that was this right here. Okay, so let's suppose that we have, let's just suppose that f is entire and bounded. Okay, so you know what entire means, right? Okay, bounded means that there exists a number m such that f of z is less than or equal to m for all z. Okay, that's what bounded means. Okay, so suppose f is entire and bounded. And I'm going to show you something really interesting. If we apply Cauchy's inequalities with n equal to 1, okay? So that would be m over r, right? Okay, so the derivative, the modulus of the derivative is less than or equal to m over r. Now, this right here, this inequality applies for, you can, it doesn't really matter, you can make the, so w could be there, okay? You can make these circles bigger and bigger, right? And you can make it even bigger. Wait, you keep on going bigger and bigger. You can make them larger, right? And still this inequality is going to hold. Now, if f is bounded though, right here, if f is bounded, then this m right here is going to work right there for this m. M is just supposed to be the maximum value on this circle of f. Okay, this m, this is the maximum value of f on this circle. On that circle, z minus w, the maximum value f of z, modulus of f of z on this circle. That's what the m is. But if f is bounded by m everywhere, then certainly it's bounded by m on every single circle like that, right? R go to infinity. And what happens when you let r go to infinity? What happens to this?
0.
Yeah, that's going to go to 0. So that means that this is less than or equal to 0. And the only way that can happen is if this is equal to 0. Okay, and then you can go back and choose other values of w. And you basically, f of z, the derivative is going to be 0 everywhere. Okay, so what happens if your derivative is 0 everywhere?
Is this
Can you
a
think
constant function?
Yeah, that means f is a constant. Okay, f is a constant. And this is known as Liouville's theorem. Okay, it's right here too. Let's see. See, it's Liouville's theorem, corollary 513. And you can see that you've got this m over r, and you just let that it goes to 0 as r goes to infinity. Okay, so if it's bounded and it's entire, then it has to be constant. Then it has to be a constant function. That's the only function. The constant function is the only function that can do that. Okay, another thing that comes from this is the fundamental theorem of algebra. Okay, which is every non-constant polynomial has a root in C. So what you do there, let me just kind of just walk you through this a little bit. So the way that this works is that it's a proof by contradiction, I'm sorry, a proof by contradiction. So you suppose that it does not have any roots. So we know that polynomials are entire functions, right? Polynomials are entire. And if you take an entire function, if you take the reciprocal of an entire function, or 1 over an entire function, it's going to be entire where it's not 0. So if it's not 0, then it's going to be entire. So if it's never 0, so we're supposing that P does not have any roots, that means it's never 0. So that means that this function here, 1 over z, is entire, which is ridiculous because it does have zeros, right? But we're just going to play along. We're supposing that P does not have any roots, no zeros. It's never 0. So that means that 1 over P of z is entire. Now, what happens with polynomials is you have a leading coefficient. So you have, like, let's say, for example, here they kind of do it generally. But let's just take an example. Let's say P of z is 3z squared. Now we'll go z to the 5th, okay? Minus 17z to the 4th plus 2, something like that, okay? So what's going to happen as the magnitude of, as this gets larger, then this 3z to the 5th dominates. Okay, by that, I mean, it's like, becomes much, much bigger than any other term. Okay, so it's in absolute value, it's going to dominate. And it's going to infinity. And so what's going to happen is that 1 over P of z gets dominated by the leading term. And that's going to go to 0. Okay, as z goes to infinity. And it's kind of a little bit tedious to show that, but, you know, I think you kind of get the idea. So, so it's basically saying, and then also if you have a, so the idea is this. So since it's going to 0, that means it's bounded out here. Okay, 1 over P of z is bounded out here. And then because this is closed, okay, because it's going to 0, it's bounded out here. So you can find, so that's the definition of going to, we're not going to get into that. And then this part right here is closed and bounded. And that implies that 1 over P of z is bounded here. Okay. And then say maybe this is bounded, say, maybe this one's bounded by M1, and this one is bounded by, say, M2. Then overall, that one's going to be bounded by the maximum of M1 and M2. So this is closed and bounded. I mean, this is entire and bounded, which means what? It's bounded and entire, which means it's constant, right? Which is a contradiction. So basically, we proved the fundamental theorem of algebra. Yay. Okay, so let's see here. Let's take a look at some of your homework exercises. There's one more thing that I kind of want to improve. Yeah, I want to do one more thing. Okay. Okay, so f is entire, and let's say that f of z in modulus is less than or equal to a times the modulus of z plus b for all z's in the complex plane. Okay, so we're assuming that, and I want to prove from this that f is a linear polynomial. Whoa. Okay, so so f is entire, and it's also the modulus of f of z is less than or equal to a times the modulus of z plus b. So this a and b, I guess they have to be real in order for this to work. Yeah, a and b have to be real numbers, but they could be negative, but probably not going to be negative. But they just say that that happens. And we want to show that f is a linear polynomial. And linear polynomials are going to look like for an example of a linear polynomial, well, it's going to look something like this, az plus b, right? Linear polynomial. Polynomial of degree 1. Okay, so let's go ahead and do that. Let's go ahead and I'll kind of show you the proof. So here, I'm going to do Cauchy's inequality with n equal to 2. Okay, so let me go back to where we have it written down. So it is where is it? This one right here. Cauchy's inequalities for n equals 2. So this is 2 second derivative 2 factorial m r over r squared. Okay, so the second derivative modulus is less than or equal to 2 m over r squared. Okay, but then we know that that this is less than or equal to that, right? So that means the maximum is less than or equal to that. Okay, So if this is W right there, so this is, I want to just let, so you just choose each W individually in the complex numbers. So let's say W is right there, okay? Then the idea is you want to draw, you want to take a circle that's bigger than twice this radius here. You want, so like this radius here, you want it more than that, right? You want it over here. And if you do that, then you start getting, so I'm going to, for r is greater than 2 times the magnitude of W, then what happens is this distance here is more than r. Then that means then modulus of z is greater than or equal to r. Or modulus of z is greater than r. Okay? No. R over 2, I'm sorry. Okay. So that's going to be, for this right here, this is going to be less than or equal to this part right here, r over 2. Okay, and as r goes to infinity, what happens to this? Well, you just have an r. What's that?
If it's 0.
Yeah, that's going to go to 0. Okay, so that means that the second derivative is 0. Okay, so this is just similar to what we did before, right? And then the second derivative is 0 everywhere, which means that the first derivative has to be a constant, which means that the original one is taking antiderivatives. That means that the original one has to be az plus b, which is a linear polynomial. So we've proven this right there. Okay, so it looks like we're out of time. So that was chapter 5, pretty much. So we'll meet again on Friday. And so if you have any questions or whatnot, let me know about it on Friday. We also have exam 2